Vande Matram. Hello friends, मैं Anand from Anand Techno Solution. Today I am going to discuss after switch on how you find the 5G cell. This video is very important if you want to understand really how you search the 5G cell. If you want to get more video from my channel, please subscribe it and click on bell button to enable email notification. When you first time power on the device, your device got into out of a coverage and try to detect a search new cell. UE mobile doesn't have any idea on which frequency it has to try to camp on. So it may have to do some kind of blind search. Suppose UE is off, you have just power on the mobile, it will scan all the frequency. Here you can see two type of frequency scan, SLS and DBS. SLS storage list search. It check and scan those frequency which was stored in mobile before switch on. That means मोबाइल स्विच ऑन होने से पहले जिन फ्रीक्वेंसी का यूज हुआ था तो यूई पहले उन सारे फ्रीक्वेंसी को स्कैन करेगा जो मोबाइल में स्टोरेड है. DBS क्या है? Deviated Band Search. If after SLS search you didn't find any cell, then you will start DBS search where you will scan all the frequency for whole band. अगर स्टोरेज लिस्ट सर्च में यूई को कोई फिजिकल सेल आईडी नहीं मिला, देन यूई विल स्टार्ट ए DBS सर्च. इन दिस केस you will scan all the frequency for the whole band. For example, let's assume that your device support 5G band N1, N2, N20. So in this case, for a scan, UE will use NR ARFCN range for N1, N2, N20. अगर मैं FDD band N1 की बात करें तो band N1 range is 422,000 to 434,000. Band N20 range is 158200 to 164200. And band N2 range की बात करें तो it is 386,000 to 398,000. So here, what is the main target of UE? Main target of UE is to find a suitable physical cell ID to camp on the cell. Here you can see in this step, UE tune to each and every channel that it support and measure RSSI. RSI is simply a measurement of whatever energy power it can measure. This measurement doesn't require any channel coding process. In this step, you doesn't need to know anything about the network. At this step, you doesn't try to decode the synchronization reference signal to detect the physical cell ID. It just measures the power of each channel. It create a list of each channel number with measure RSSI. Suppose that in step 1 UE got 9 frequency which RSSI value is measured and make a list of the 9 frequency. अब step 2 में क्या होगा? Now UE will go through the list from step 1. Step 1 में जो list में 9 frequency थे, right? So and now it figure out all the channel which show RSI value greater than the threshold value. So this threshold value is also up to the UE chipset implementation, not determined by 3GPP. So out of 9 in step 2 you got a 3 frequency. You can see in this log, I have taken this log for the understanding purpose. Here you can see that in 5G mobile there is one component is N1 L1CL. This is physical component. It send a frequency scan request with NR ARFCN range is 386,000 to 398,000. For band 2, it send a frequency scan request. Now N1 L1CL physical component, N1 L1CL component got the result where a scan started from 386,000 and total ARFCN scan is 28. Out of 28 ARFCN, 3 best ARFCN is 386,000, 386670 and 399,000. This 3 frequency got for band 2. N1 L1CL send frequency scan request with NR ARFCN range 158,200 to 164,200. For band is N20. And N1 L1CL got the result where a scan started from 158,200 and total NR FCN scan is 16, and out of 16 ARFCN, 3 best ARFCN is 158.200, 159.000, 160.000. So these 3 frequency got for N20. Again, N1 L1CL sent frequency scan request with NRFCN range 422.000 to 434.000 for band N1, and N1 L1CL got the result where scan started from 422.000 and total NR ARFCN scan is 16, and out of the 60 ARFCN, 3 best ARFCN is 422.000, 423.200, 430.000. So these 3 frequency got in N1 band. So here in step 1 process is completed. In step 1 physical layer will prepare the list of 9 frequency, right? 9 frequency I have told. So in step 2 में मैंने क्या बोला था? It will figure out all the channel which show RSI value greater than threshold value. So suppose in step 2 again 5 layer component will be prepare the list of frequency which RSI value is greater than the threshold value. So in this step total 3 frequency is here which RSI value is greater than threshold value. 5G ARFCN range is NRFCN 159.000 for band 20, 386670 for band N2, and 390.000 for band N2. So band N2 2 frequency and band 20 1 frequency is there which RSI value is greater than threshold value. So here a step 2 process is completed. Till step 2 LTE and 5G process is same. A step 3 process is little different from LT process. This step is little complicated, so it will take time to understand the complete process. UE do synchronization process and decode Ssb block by scanning synchronization raster. Again I am telling, UE do synchronization process and decode Ssb block by scanning synchronization raster. Keep in your mind 2 words, Ssb block and synchronization raster. Again, now from a step 2 list, में total how many frequency was there? 3. So one by one you will start synchronization process for all 3 frequency. In step 2 we can see first preferred NR ARFCN is 386670. So you will scan NR ARFCN 386670 and will try to get a suitable Ssb. Again I am telling, you will scan NR ARFCN 386670 and will try to get a suitable Ssb. Again Ssb is coming. Keep in your mind Ssb and synchronization raster. Here in step 3 lot of question is coming. जैसा कि मैंने बोला था, you do synchronization process and decode Ssb block by scanning synchronization raster. Ssb block and synchronization raster. That means decoding the Ssb block by scanning synchronization raster. A second मैंने जो बोला था, you will scan NR ARFCN and will try to get a suitable Ssb. So question is that how 5G step 3 is different from LTE step 3. Second question is why we are trying to decode Ssb. What is synchronization raster? How UE will find 5G NR Ssb. Fifth question is what is frequency and time domain location of Ssb. First question is how 5G step 3 is different from LTE step 3. I have uploaded one videos for this. So below a link is there, so you can click and you can watch LTE cell search process there. So 5G NR is same as LTE. First signal received by the UE at power on is PSS and SSS from the cell. In LTE, after power on, first UE do frequency scan process followed by step 1 and step 2. Once 5 layer prepare a list of ARFCN which RSI value is greater than the threshold value and send this frequency to the upper layer. Now upper layer, what will do? Upper layer one by one frequency sent to the 5 layer to decode physical cell ID. So for decode the physical cell ID, first UE need to decode PSS and SSS. So in LT, PSS and SSS location is fixed and always located at center of the carrier. Again I am telling you, in LT, PSS and SSS location is fixed and always located at center of the carrier, center of the frequency. If you want to see cell search process in LT, please watch my uploaded video and link is below. We are talking about NR. In NR, cell search process in non-standalone mode and standalone mode is different. When NR is activated in non-standalone mode, UE doesn't need to do a blind search for Ssb, since the frequency, subcarrier, spacing, etc. are configured by LT in RRC connection reconfiguration message. NSA part we will see later. In this video only focus on a standalone mode case. मैंने क्या बोला कि NR जो सेल सर्च प्रोसेस है नॉन स्टैंड एलोन मोड के लिए और स्टैंड एलोन मोड के लिए, दोनों के लिए डिफरेंट है. जब NR 5G जब एक्टिवेट होता है नॉन स्टैंड एलोन मोड में, तो UE को कोई ब्लाइंड सर्च करने की जरूरत नहीं होती, क्योंकि वो सारा इन्फॉर्मेशन RRC रिकन्फिगरेशन के थ्रू UE को मिल जाता है. About the frequency, subcarrier spacing, all information you get it in RRC reconfiguration message, so that no need to do the blind search. तो फ्रेंड्स आज का वीडियो मैं यहीं पे समाप्त करता हूँ. थैंक्स फॉर वाचिंग दिस वीडियो. अगर आपको मेरा वीडियो पसंद आया हो तो प्लीज़ लाइक एंड कमेंट करें, और अगर आप मेरे चैनल पे नए हैं तो प्लीज़ सब्सक्राइब करें, क्योंकि मैं हमेशा कुछ नए टॉपिक पे वीडियो लाता रहता हूँ और उसका नोटिफिकेशन आपको मिलता रहेगा. सो थैंक्स फॉर वाचिंग वीडियो. But in a standalone mode, blind search is required. Why blind search is required? UE scan blindly and detect Ssb, since UE need to detect this before it get any RRC. Because पावर होने के बाद UE को उस टाइम पे कोई RRC मैसेज नहीं होता, कोई मीब नहीं मिलता, कोई सिब नहीं मिलता. So UE need to do blindly and try to find the Ssb location. Right? Because of that, we are doing blindly search in a standalone mode. Why UE trying to decode Ssb? Because UE want to decode PSS and SSS to find the physical cell ID, and PSS and SSS exist in Ssb block, so that UE want to decode Ssb first. UE need to search Ssb based on ARC and raster. Again ARC and raster come. Now here concept will come of global synchronization number, channel raster, synchronization raster. What is the channel number? What is channel raster? What is synchronization raster? What is GSCN? So a lot of the question is coming one by one. I am trying to decode all the question. So channel raster first is that. Channel raster concept is also in LT. LT में भी ये concept है channel raster का. So channel raster for LT is 100 kilohertz for all band, and center frequency must be a whole number multiple of 100 kilohertz. Again I am repeating, center frequency must be a whole number multiple of 100 kilohertz. So इसका मतलब है in LT, PSS and SSS exist in central frequency. So how UE will reach on central frequency? UE will scan the whole the band in multiple of 100 kilohertz raster, where PSS and SSS exist, because in central frequency PSS and SSS exist in the LT, right? So suppose that one frequency bandwidth is there, so in every 100 kilohertz it will try to scan, and it will reach to the central frequency. Once it will reach to the central frequency, you will get it the PSS and SSS and PVCH, so that you scan whole band in a multiple of 100 kilohertz in LT. So channel raster in LT is 100 kilohertz. So what is synchronization raster in 5G NR? Concept of channel raster in 5G NR is the same as that of LT. But if frequency interval या channel raster is 100 kilohertz like LT, so search time will be a longer and higher performance requirement for the terminal. right? LT में 100 kilohertz है, but in 5G frequency range is very high. So in that case, if it will try to scan on every 100 kilohertz channel raster, it will take too much time. So it will affect the UE performance. 5G frequency is very narrow. Therefore, in order to search the PSS and SSS faster, 5G frequency is very narrow, so it need to be searched very fast. So 5G NR adopt a different approach from LT. Ssb position is not fixed because of a different subcarrier spacing. There is limited set of possible location in each band, also called a synchronization raster. So SSB limited possible location पे exist करता है. SSB limited possible location पे exist करता है. इस possible location को ही synchronization raster कहते हैं. UE perform Ssb search in this sparse and specific possible location. Similar to the understanding of the channel raster, synchronization raster can be considered as a minimum frequency interval of a central frequency point of Ssb. Here you can see that, suppose that Ssb is available on this part. Here it is available. Now you want to search the Ssb. So this small part, we can say that this is a synchronization raster. So every time it will scan and will try to reach the Ssb central point. At Ssb central point it will try to reach. So it will scan this small part. A small part, you can say that granularity, yeah, you can say that synchronization raster, yeah, a small width it will try to scan. So and every step it will scan and it will come to reach this central point of Ssb. So this is called SS raster. Yeah, you can say that GSCN. Yeah, this is also SS reference point. SS REF also we can say that this central point of Ssb is SS REF. Yeah, you can say that GSCN. ये small part को scan करते हुए you will search to the center frequency point of Ssb. So this small part is synchronization raster. और जो center frequency of Ssb is GSCN या SSREF. GSCN या SSREF. What is GSCN? Again same thing. If UE need to search Ssb based on AFCN raster, it would take a long time. Since AFCN raster is very narrow, so it would be good to define Ssb searching frequency in wider step. This is uses and purpose of GSCN. So we are using the wider step, that is synchronization raster. We are scanning the full bandwidth in synchronization raster, whatever width is there. After scanning, we are trying to figure out the GSCN. We are able to find out the GSCN value, GSCN point of the Ssb location. So now question is that how much raster frequency width can be used to scan the whole frequency bandwidth. What is the width is required? It will scan on the frequency synchronization raster. It will scan the one specific width. So what is the width of that scanning? So if it will use 100 kilohertz like LT, if it will use 100 kilohertz raster to scan, it will take a long time, right? So for 5G NR need to use wider frequency width to scan whole frequency. Here you can see that position of PSS and SSS in LT and 5G NR in the carrier. Position of Ssb is not fixed in 5G NR. You can see that it is not a central frequency. There is not, maybe Ssb can be placed here, maybe it will be placed on below. So position is not fixed for the Ssb. But in LT, PSS and SSS exist on central frequency point. So you will know that location of PSS, SSS in LT. But in 5G NR, you doesn't know the Ssb. So what you will do, it will use the small width and it will try to reach on Ssb of central frequency point, that is SSREF. Yeah, you can say that GSCN. Now in this image, Ssb block is available here in this point, and this is a frequency domain, this is time domain. Center frequency of Ssb is a multiple of synchronization raster. Again I am telling, central frequency of Ssb central frequency of SSB is multiplied of synchronization raster. अब synchronization raster का जो साइज है उसी के multiplied में SSB is existing in frequency and time domain, so that if know the width, if know the formula, then we can calculate it and you is able to search the SSB location. So position of SSB synchronization signal is variable and doesn't necessarily have to be placed at a center frequency. So ये जरूरत नहीं है कि वो सेंट्रल फ्रीक्वेंसी पे SSB हो, कहीं भी हो सकता है फ्रीक्वेंसी और टाइम डोमेन लोकेशन में. So in every synchronization raster, this a small size it will scan. One suppose that a small size is 1 megahertz. 1 megahertz is not there. It is more than 1 megahertz. Synchronization raster size is that. Suppose that 1 megahertz is there. So in every 1 megahertz, it will try to scan and it will reach to the central frequency point of SSB. So in 5G NR, what is the raster value? Yeah, you can say that what is the step size for the scan the frequency. In example, suppose that we are taking 3.7 and 4.5 gigahertz band, that means FR1 frequency we are taking. Then SSB can be placed every 1.44 megahertz step size. SSB can be placed every 1.44 megahertz step size. But if it is FR2, that means 28 gigahertz band, then SSB can be placed at 17.28 megahertz step size. So SSB will be placed at 70.28 megahertz step size. Synchronization raster divide a carrier bandwidth in finite number of locations where SSB can be deployed and all possible SSB center frequency point across the NR spectrum called GSCN. Again I am repeating. Synchronization raster divide carrier bandwidth into finite number of locations where SSB can be deployed and all possible SSB center frequency point across the NR spectrum called GSCN, Global Synchronization Channel Number. तो फ्रेंड्स, आज का वीडियो मैं यहीं पे समाप्त करता हूँ. थैंक्स फॉर वाचिंग दिस वीडियो. अगर आपको मेरा वीडियो पसंद आया हो तो प्लीज़ लाइक एंड कमेंट करें, और अगर आप मेरे चैनल पर नए हैं तो प्लीज़ सब्सक्राइब करें, क्योंकि मैं हमेशा कुछ नए टॉपिक पे वीडियो लाता रहता हूं और उसका नोटिफिकेशन आपको मिलता रहेगा. सो थैंक्स फॉर वाचिंग वीडियो. Now we can see the relationship between SSB center frequency point and GSCN. We will try to understand the conversion from SSB reference to GSCN and GSCN to the SS reference. So in this table you can see that range of frequency, SS block frequency position, that is SSRF, GSCN, and range of GSCN. Here you can see that if range of frequency is 0 to 3000 megahertz, SS block frequency position, SS reference will calculate from this formula, n into 1200 kilohertz. 1200 you can say that 1.2 megahertz plus m into 15 kilohertz, that is SSRF. This is SSRF calculation formula. SSRF equal to n into 1200 kilohertz plus m into 15 kilohertz. This is SS block frequency position, that is SSRF. N value is 1 to 2499, M value is 135. So we'll try to understand that what is the means of N, what is the means of M. So here 1200 kilohertz means 1.2 megahertz is frequency raster. You can say the synchronization raster. So we'll try to scan whole bandwidth on 1.2 megahertz a step. 1.2 megahertz step it will scan. So on every 1.2 megahertz step you will try to find the location of SSB. GSCN, how we calculate the GSCN? If we know the value of N and M value is fixed 135, but N value, if we know the N n value, then we calculate the GSN 3n plus m minus 3 by 2. This is formula to calculate the GSN for 0 to 3000 megahertz range. So if suppose that we want to calculate the range of GSN, so range of GSN is 2 to 7498. 2 is the minimum value, maximum value is 7498. Suppose the n equal to 1, m equal to 1. So here you can see that 3 plus 1 minus 3 by 2, that means GSN equal to 2. If n equal to 1, in second step, second scan is happening, n equal to 1, m equal to 3, that means GSN equal to 3, right? N equal to 1, that means 3, 3 minus 3 by 2, that means 0, 3, n equal to 3, GSN equal to 3. As the same, if n equal to 249, maximum value of n equal to 2499, right? If we can see that if n equal to 2499 and m value is also maximum 1355, so m equal to 5, then GSN value equal to 7498. So range of GSN is 2 to 7498 for this frequency range. On same way, we can calculate the SSRF, you can say that SS block frequency position for range of frequency 3000 to 24250. So in this range, raster size, you can say that synchronization raster size is 1.44 megahertz. So the every 1.44 megahertz step, you will try to find the Ssb position. So this formula is SS reference, SS block frequency position, SS reference position formula is 3000 plus n into 1.44 megahertz and n equal to 0 to 14756, right? And GSN formula is 7499 plus n. If suppose that n value we know that, then we'll add the n value and we can calculate the range of GSN 7499 to 22255. For frequency range 24250, this gigahertz, calculation is formula is this 24250.08 megahertz plus n into here raster size. You can see that in this case raster size, you can say that synchronization raster step size is 17.28 megahertz. So every 17.2 megahertz step size, you will try to find the Ssb position, and formula is 24250.08 megahertz plus n into 17.28 megahertz. 70.28 is synchronization raster size. In value is belong to the 0 to 4383, right? And GSN formula is 22256 plus n. So range of GSN is 22256 to 26639. So this is the range of GSN. So in this example, you can see that 5G NR, suppose that SS reference frequency. I have taken the one example. Here you can see that if suppose that SS block frequency position SSRF equal to 3325.44 megahertz, then how you will calculate it GSN, right? So you can see that it is belong to the second range, right? 3000 to 24250. It is coming belong to this range. So formula is 3000 plus n into 1.44 equal to SS reference equal to 3325.44, right? So we will calculate the n value here. So n value is around 226, right? 226. So how we'll calculate the GSN? GSN formula is 7499 plus n. N value is 226. Then our GSN value is 7725. So this is the GSN for SS reference frequency 3325.44 megahertz. So this frequency के लिए GSN 77725 हो गया. अब इस पार्ट को थोड़ा सा देख लेते हैं. इन एंड एम मैंने बोला था, राइट? सो सपोज दैट फर्स्ट फ्रीक्वेंसी आई एम टेकिंग फर्स्ट 0 to 3000. सो फार्मूला इज n into 1200 kilohertz plus m into 50 kilohertz. So 1200, that is 1.2 megahertz is our synchronization raster, right? So what will be the first scan? If you will do the first scan, then how it will do? Suppose that this frequency is there and n is equal to 1200. So n is equal to 1200, n is equal to suppose that 1 and m is equal to 1, right? So 12. So first it will scan 1200 plus 15 kilohertz, right? This is the first scan, right? Second scan will be व्हेन m इक्वल टू 3, m इक्वल टू जब 3 होगा तब क्या होगा, 3 होगा तो n इक्वल टू 1, n इक्वल टू 1, m इक्वल टू 3. So again 1200 kilohertz plus m equal to 3, then 150 kilohertz this time will do, right? Third scan will happen, n equal to same 1 and m equal to 5, right? So 5 into 50, the 1200 and 250 kilohertz. Same way it will, fourth scan will, n value will be changed this time, n is equal to 2 and m equal to 1. So again it this time scan will be 2 into 1200, that means 2400 kilohertz, 2.4. So 2400 and 15 kilohertz, 2400 150 kilohertz, 2400 250 kilohertz. So this type of a scan will happen for 0 to 3000 megahertz. So Ssb follow GSCN raster in standalone mode. Here you can see that if Ssb is available in this position in time and frequency domain, right? In time and frequency domain, Ssb is available here. So scan this full bandwidth in order with a special granularity. Granularity means a small part in synchronization raster. In every small part it will try to scan it, and a special granularity GSC in order to find and understand Ssb block. Every granularity, every step it will scan and will reach to the Ssb central frequency point. And we have another formula to calculate the time domain location, in which time domain location point Ssb is available. So if you get a time domain location, if you get a frequency domain location, then you can know that exact location of Ssb. Now I am going to finish this video. Till now I have covered 80% part of Ssb search process. In next video, that will be a part 4, you will get a complete understanding of Ssb search process. I have taken this image from part 1 video. As you know, in first part video I have covered step 1 and step 2 process. A step 3 process I have divided in 2 parts. First part is Ssb search process, which is covered in part 2, 3 and 4 videos. And next second part is 5G cell search process, will cover in video 5 and 6. So total 6 video I will upload for 5G cell search process. This one is the part 3. So please watch my next video for part 4, where we will use the formula for time and frequency domain to calculate the Ssb location.
Thank you very much to watch this video. If you enjoyed this video and want to hear from me again, be sure to hit that like and subscribe button before you go. If you have any query or suggestion, please comment below and I will try to explain in next video. Thanks you.
When you first time power on the device, mobile scan all the frequency and try to detect Ssb location in frequency and time domain. To reach on correct position of Ssb, you should know SSREF, that is Ssb center frequency location and time domain location. For band N2, frequency range is 1930 to 1990 MHz and SSREF location will start from 1932.05 to 1987.45 for band N2. You can see first scan SSREF location is 1932.05, second scan and SSREF location is 1932.15, third scan SSREF location is 1932.25, fourth scan SSREF location is 1933.25, like that. In the time domain, Ssb will start from position 2, 8, 16 and 22 wavelength symbol. Let's assume Ssb placed at this SSREF location and mobile doesn't know about Ssb location. Let's see how mobile search the Ssb location in frequency and time domain location. Finally, UE got Ssb location, that is 1933.35 megahertz SSREF, and another Ssb got on 1987.45 megahertz. So this frequency, two frequency point, UE got the Ssb location after frequency scan. Now I will try to explore this animated video in depth. Now I will try to explore this animated video in depth. But now all of you must have watched 3 videos for 5G cell search process, and hope you have understood the Ssb search process well, and now you understand the meaning of SSREF, GSCN and Synchronization Raster. In this video I am going to explain how SSREF, GSCN, 5G ARFCN, frequency scan and Synchronization Raster are related to each other. Before starting this video, please help yourself to subscribe to the channel. Once the video start in 2D 3D format, the channel will convert to a premium basis from December 2021. If you subscribe before December, your membership will be free for a lifetime. So the decision in your hand. Thanks. A story start from 5G band N2, which ARCN range is 386,000 to 398,000. In first video, you have seen preferred ARFCN was 386670, which was found after UE scan. So now question is that how UE scan band N2 and found ARFCN, that is 386670, where Ssb is present in frequency domain location, that is SSREF. So how UE scan? Now answer is that I will try to elaborate this answer. So if UE support band N2, that means UE know ARFCN range, and from ARFCN UE can calculate GSCN and its GSCN range. Here now we will try to correlate to each other with all the parameter like GSCN, SSREF, ARFCN, frequency scan, Synchronization Raster, and the meaning of M and N value. I have taken the example of 5G band N2. 5G ARFCN range is fixed. NRFCN range, that is 386,000 to 398,000. GSCN range is 4829 to 4969. That is step 1 is the step. SSREF range is 1932.05 to 1987.45 megahertz. So in this table, these parameters are related to each other. From ARCN you can calculate and find GSCN and Ssb frequency center point, that is SSREF. Yeah, from GSCN we can calculate SSREF, yeah, 5G ARFCN. So this is reciprocal to each other. So in this table you can see this frequency range for band N2. Frequency range is 1930 megahertz to 1990 megahertz. This is the range of band N2. And for this range, GSCN calculate from that formula is calculation formula is 3n plus m minus 3 by 2, and SSREF calculation formula is n into 1200 kilohertz plus m into 15 kilohertz, where n belongs to the 12499 and m value is 135. So in this table I'm showing you by using GSCN how we can find SSREF value and 5G ARFCN value. GSCN range is 4829 to 4969, right? So the first GSCN value is 4829 and 1 is the step. So that means it will increase by a step 1. That means like 4829, 4830, 4831, like that it will increase. So 4829 to 4969. So total scan is 140. How it is 140? Just subtract 4969 minus 4829, that is 140. So total scan is 140. That means every step. So 140 times it will try to scan. So this is the GSCN calculation formula for the first range. For this formula we will calculate the n value. So once n value we will calculate, we will find the SSREF point, that is the Ssb central position, that is SSREF. After getting SSREF value, we will calculate the 5G AFCN value by using this formula, where FREF equal to SSREF, that is Ssb central frequency point, and FREF offset value is the first frequency where band N2 is going to start. What is the band to N2 range? That is 1930 megahertz to 1990 megahertz. So that first value, that is offset value, is 1930. NREF offset value is same as frequency. NRAFCN range is 386,000 to 398,000. So what will be the offset value? Offset value will be 386,000, right? And del F global is the frequency raster, that is 5 kilohertz. That is the size of a small you can granularity, a small part, that is 5 kilohertz. So one by one we will calculate the SSREF and ARFCN. So first GSCN value is 4829, right, for band N2. So first a scan is the first, and M value is 135. So first M is equal to now 1 for the first scan. So GSCN formula is 3n plus m minus 3 by 2. So here we will calculate the n value. So here GSN value is 4829, 3n plus m is equal to 1 minus 3 by 2. So n is equal to 1610. Now n is equal to 1610 and m is equal to 1. So what will be the value of SSREF? SSREF value is n into 1200 kilohertz plus m into 50 kilohertz. N is equal to 1610 into 1200 plus 1 into 50, that is 1932.05 megahertz. So this is the first frequency, that is SSREF, that is found in first scan. But in this position Ssb block is not present. I will calculate the AFCN value, FREF minus FREF offset by del F global plus NREF offset. मैंने बताया था ना, FREF that is SSREF. So this is 1932.05 which is got, right, SSREF, and minus offset value which where band N2 is going to start 1930 by 5 kilohertz, that is frequency raster, right, so del F global. So I have divided, converted in megahertz, that is 0.005 plus this is offset value for the AFCN 386,000. So that calculation is first AFCN which is calculated for the first scan, that is 386,410. So this is the first scan. In first scan got AFCN value is 386,410 and frequency is 1932.05 megahertz. But first scan Ssb is not observed, right? So that it will go for the second scan. In first video you have seen, first video what was the preferred AFCN? 386,670 where Ssb was present, but here 386,410 is coming. So here Ssb is not present, so it will go for the second scan. In second scan, that is 4830, because it will increase by step 1, right? In first scan it was 4829, now it is 4830. Second scan m value is 135, 1 is done. Second scan m value is 3. So here we will calculate the n value. For n value is 1610, right? After putting this formula n and m, n value is equal to 1610. Now n is equal to 1610, m is equal to 3. Then SSREF will put in this formula n and m value. Then we will calculate 1932.15, right? So this is the second scan frequency which UE observed, that is SSREF position. Now we will calculate the AFCN range, AFCN value for this frequency. So for this frequency we will put in this formula FREF minus FREF offset by del F global plus NREF offset. FREF is 1932.15, that is SSREF is FREF. So this 1932.215 plus FREF offset, that is a band N2 first value is 1930, where band N2 is going to start, and 0.005, that is we have converted the frequency raster in megahertz, plus NREF offset 386,000. So this 386,430, this is the second scan AFCN value. So in second scan also Ssb is not located, so it will go for the next scan. So next scan is third scan is 4831, again one step increases, right? So previous that 4830, now it is 4831. So in third scan m is equal to now 5, because 1 is done, 3 is done, now 5 m is equal to 5. So in GSN formula we will put m value and we will try to calculate the n value. So in n value we will calculate n value is again 1610. So now n is equal to 1610, m is equal to 5, that SSREF equal to n into 1200 plus m into 50. So SSREF position third formula is 1932.25. This is the third frequency, third scan, third frequency, that is 1932.25 SSREF is. Now we will calculate the AFCN. So what will be the AFCN for this frequency? FREF minus FREF, also same formula, we will put 1932.25 minus 1930 by 0.005 plus 386,000, so 386,450. So this is the third scan. So in third scan also AFCN is Ssb is not located. So again it will go for the fourth scan. The fourth scan GSN value is 4832. A scan is fourth, m value is again 1, because 135, right? 135 is done, so again it will repeat from 1. So m value is 1. GSN formula we will put the value m and we will calculate the n value. So now n value is changed. Now L value is 1611. दैट इसके पहले जो तीन स्कैन हुए थे उसमें वैल्यू क्या था इनका, दैट इज 1610. नाउ इन फोर्थ स्कैन इन वैल्यू इज 1611. सो नाउ इन इज 1611, m is equal to 1. Then SSREF formula we will put n and m and we'll try to find out. Then SSREF value is 1933.25 megahertz. So this is the SSREF location, that is Ssb location center point, but Ssb is also not located here. So we will convert in AFCN value. So AFCN formula is this one. So we'll put FREF, that is 1933.25, offset value, that is band into first frequency, that is 1930 by 0.005 plus 386, that is AFCN offset value. So that 386,000, so 386650. This is the fourth scan where also Ssb is not located, right? So fourth scan, and now it will go for the fifth scan. In fifth scan value is GSN value is now value is 4833. A scan is fifth, m value is changed 135, right? So now 3 again. So GSN value formula is that 3n plus m minus 3 by 2. So we will put the m value and we will calculate the n value is 1611. So n is equal to 1611, m is equal to 3. SSREF will calculate n into 1200 plus m into 50. That SSREF value is equal to 1933.35 megahertz. So now what is the AFCN value? AFCN will calculate from this formula, same formula, FREF minus offset del F global ni. So what is the reference? FREF 1933.35, that is SSREF. So same, and 1930, that is a band into first frequency by 0.005 plus 386,000, that is the AFCN offset value. So here it is 386670. So now finally UE got 5G AFCN 386670 and respective SSREF, that is frequency is SSREF frequency is 1933.35 megahertz value, where Ssb is located in this position, whatever I have shown in the first video. So same frequency got after fifth scan. So here in this position Ssb is located 386670 AFCN value, and SSREF value is 1933.35 megahertz. This is the SSRF frequency position. So in this position Ssb is located. So you have remembered I had shown you in the first video what was the preferred AFCN which was found during the frequency scan. That was the same AFCN 386670. So now you understand how you search and scan the frequency. So now अभी मैं क्या करूँगा कि now just see the last 3 scan because total scan is 140 scan, right? So मैंने 5 scan में 5th scan में मुझे मिल गया. So total scan 140, right? So see the last 3 scan 138, 139 and 140th scan. So now see the third last, that is 138 scan, and find out the SSRF location and AFCN value. So 130th scan GSCN value is 4967 and the scan is 138, m value is 1. So we will calculate the n value. N value is, when we will put the m value, that is 1, so n value is 1656. Now n value is 1656, m is equal to 1, then SSRF location, frequency location is n into 1200 plus m into 50. That SSRF location will be just put in this n and m value, then it will come 1987.25 megahertz. 1987.25 megahertz. Now what will the ARCN value? ARCN value is same, FREF minus FREF offset by del F global plus NREF offset. FREF is the SSREF, right? So same, I will put 1987.25 minus FREF offset value is the first frequency of the band into, that is 1930, and by 0.00 frequency raster we have converted in megahertz, and offset value of AFCN, that is the 386000, that is the offset value of the band into. So that after that calculation it came 397450. So this is a 138 scan. Now we will go for 139th scan. The 139th scan, that GSN value is 4968 and m value is equal to 3. So GSN formula will put m value, m is equal to 3, and we will calculate the n, that is 1656. Now n is equal to 1656, m is equal to 3, then SSRF will put n and m, then here SSRF position will be 1987.35 megahertz. So we'll calculate the AFCN value. AFCN value same, FREF minus FREF offset del F global. So we'll put the FREF, that is 1987.35 minus 1930 and 0.005 and 386000. Here 397470 it's coming. So here also Ssb is not located here. Now see the last 140th scan, find out the SSRF location and AFCN. So 140th scan, GSN value is 4969, that is the last GSN value. A scan is 140th, m is equal to 5. We will calculate the formula, n and m value will put, and calculate the n value, that is n value is 1656. So now n is 1656, m is equal to 5. SSRF is will put in and m value, so it will come around 1987.45 megahertz, that is SSRF location. Ssb frequency location is 1987.45 megahertz, and AFCN value is will put the formula FREF and FREF offset del F global 1987.45 minus 1930 0.005. So here it will come, AFCN is 397,490. This is AFCN and frequency is 1987.45 megahertz. So in the जो मैंने एनिमेटेड वीडियो दिखाया था, राइट, उसमें 2 पोजीशन SSB वाज लोकेटेड, राइट. सो द लास्ट SSB इज लोकेटेड एट SSRF लोकेशन इज 1987.45 मेगाहर्ट्ज which AFCN value is 397,490. सो हमें 2 पोजीशन पे SSB लोकेटेड था, राइट. एक पोजीशन था 1987.45 मेगाहर्ट्ज, दैट इज AFCN value is 397,490, और एक फर्स्ट स्कैन मुझे मिला था that was 386670, that SSRF SSB central position was 1933.35 megahertz. So इस तरीके से उस स्कैन में मुझे 2 SSB मिला था. So this is the way to calculate and find the SSRF location and AFCN value. So in this way to calculate and find the SSRF location and AFCN value. So in this way, UE scan the frequency raster one by one and try to reach on the Ssb central frequency location, that is the SSRF. Now we have got a frequency location for Ssb, that is SSRF. Next we will see the time domain location, how UE find the Ssb position on the time domain. So time domain location, in the time domain where Ssb is located, which OFDM symbol will start for Ssb. So in the time domain, OFDM location depend on subcarrier spacing and frequency range. Again I am telling, in time domain OFDM location depend on subcarrier spacing and frequency range, because 15, 30 different subcarrier spacing is there. But I have taken example of some cases, so that in case A you can see that for a frequency less than 3 GHz, अगर वो 3 GHz से लेस है, then subcarrier spacing जो है 15 kHz है, 15 kHz है, then formula to calculate the start position of OFDM is 28 plus 14n. 28 plus 14n. So this is formula to calculate the OFDM position for the SSB. So if and n equal to 0 and 1 है, फिक्स है वैल्यू n equal to 0 and 1. So तो पोजीशन क्या होगा SSB का स्टार्ट करने का पोजीशन, वो पोजीशन होगा 28 16 22, 28 16 22 वेयर SSB विल स्टार्ट. L max इक्वल टू 4, मतलब 4 SSB वहाँ रेडिएट होगा, 4 SSB वहाँ लोकेटेड होगा उस फ्रीक्वेंसी बैंडविड्थ पे, बैंड N2 के लिए अगर बात करें तो जो फ्रीक्वेंसी है. सो L max equal to 4. So OFDM symbol number indicating the start position of each Ssb block transmission is 28 16 22 where Ssb will start, and 4 position Ssb will be located. But if frequency is greater than 3 and less than 6 GHz, so n value जो है उसमें क्या था, लेस देन 3 GHz, तो n इक्वल टू 0 एंड 1 था. बट फ्रीक्वेंसी ग्रेटर देन 3 और लेस देन 6 GHz, तो n इक्वल टू क्या होगा, 0 1 2 3 होगा. तो पोजीशन जो है वो ज़्यादा होगा, राइट, SSB. सो वील यूज द सेम फार्मूला टू कैलकुलेट द पोजीशन ऑफ OFDM 2814n, एंड OFDM स्टार्ट सैम्बल विल बी 28 60 22 30 36 44 50. सो L max इक्वल टू 8. सो 8 SSB लोकेटेड होगा वहाँ पे. सो SSB will take 4 consecutive OFDM position on every start, right. 4 OFDM symbol लेता है SSB. SSB will take 4 consecutive OFDM position on every start. So example, if 28 60 22 फर्स्ट जो लिया था, so start from second OFDM symbol. 2 मतलब it will start from second OFDM symbol, and मैंने बोला 4 OFDM symbol लेता है SSB. So start करेगा 2 से, तो पोजीशन क्या होगा, OFDM symbol कौन सा यूज करेगा, 2 3 4 5 यूज करेगा 1 SSB के लिए. एंड नेक्स्ट SSB start from 8th OFDM symbol and will take 4 OFDM symbol. So जब 8 से स्टार्ट करेगा उस समय क्या होगा, 8 9 10 11 OFDM symbol will use for the second SSB. उसके बाद नेक्स्ट OFDM symbol स्टार्ट होगा, फिर से कब होगा SSB स्टार्ट होगा, वो होगा 16 से स्टार्ट होगा, 16 17 18 19 4 OFDM symbol होगा. इस तरीके से ये SSB लोकेटेड होगा. सो in this way UE find the position of SSB in time domain. Now finally you got AFCN 386670 where SSB is located on SSRF position and time domain location. So this is a way to scan the frequency, scan the SSB. So in this next video we will see about SSB, what is the SSB, which type of information SSB carry, how many resource is located for SSB, where PSS, SSS and PBCH is present, how you will decode PSS and SSS and get physical cell ID, how you will decode MEEB and SIB. So a lot of the question is there, so we will see all the query question in the next video. So thanks for the watching, and thank you. Hello friends, I'm Anand from Anand Techno Solution. Today I'm going to discuss about the Ssb block in a standalone mode. In a standalone mode, in our cell search procedure follow this step: frequency search and tuning, PSS and SSS decode, PBCH decode, RIMC and OSI decode. Step 1 already I have discussed in the last part video. आपकी जानकारी के लिए मैं बता दूं 5G सेल सर्च प्रोसेस पे ऑलरेडी 4 वीडियो अपलोड कर चुका हूं, जो कि इन ऑल 4 वीडियो आई हैव डिस्कस अबाउट द फ्रीक्वेंसी स्कैन एंड SSB scan process. Till last video we got SSB location in frequency and time domain. So now in this video I am going to discuss over SSB itself. SSB block contain PSS primary synchronization signal, SSS secondary synchronization signal and PBCH that is transmitted in symbol, right? So synchronization signal PSS, SSS and PBCH are used during cell search process. So you search for the synchronization signal when scanning for cell to camp on. जब वो सेल यूई को जब सेल पे कैंप होना चाहता है उस टाइम पे सिंक्रोनाइजेशन सिग्नल की जरूरत पड़ती है. सो यूई सर्च फॉर सिंक्रोनाइजेशन सिग्नल फर्स्ट आफ्टर स्विच ऑन. So SSB block are also used for RSRP and RSRQ and SINR measurement. So SSB block is used in downlink transmission and occupying 20 resource block in frequency domain and 4 symbol in the time domain. SSB block, you can say that PBCH block include PSS, already I've told PSS, SSS, primary synchronization signal, secondary synchronization and PBCH. So as per 3GPP specified, the bandwidth of SSPBCH block is 20 resource block. So it is fixed in as per 3GPP, and UE should be support this bandwidth capability requirement for a specific operating band. So then all the UE must be capable of the received SSPBCH block. So अगर UE capable है, इस bandwidth को support करता है, जो specified bandwidth है, अगर इस capability को support करता है, then it is able to decode the SSB block. So you can say that SSB block design as per 3GPP, SSPBCH or SSB consists of 240 contiguous subcarrier. 240 contiguous, how it happened? 20 resource block, right? 20 into 12 subcarrier, 1 RB, 12 subcarrier. So 12 into 20 equal to 240 contiguous subcarrier. So subcarrier are numbered in increasing order from 0 to 239 within SSB block. So you can say here PSS occupy 127 carrier within the first evidence symbol, where SSS secondary synchronization signal occupy also 127 carrier within a third evidence symbol. So PSS occupy first order symbol and secondary synchronization signal occupy third order symbol. PBCH occupy 20 resource block within the second and fourth order symbol. So दोनों order symbol पे होता है, second and fourth, then 20 into 2, 40 resource block is for the PBCH. So PBCH also occupy 8 resource block within the third order symbol, right? So while the SSB block is transmitted using antenna port 4000. So जो SSB block is transmitted antenna port 4000 resource block on third order symbol. So resource block allocated to the PBCH accommodate both the PBCH payload and PBCH demodulation reference signal. अब 2 टर्म आ गया PBCH में, एक demodulation आ गया, PBCH demodulation, एक PBCH payload, right? So DMRS occupied 25% of the resource element allocated to PBCH. अगर PBCH को 4 RE allocate हुआ है, so out of 4 RE, 1 RE will allocate for the DMRS. So the PBCH payload has कितना payload हो गया PBCH का? So 25% will utilize for the DMRS and total कितना RB हो गया? 2 RB है, right? Second and fourth order symbol 20 RB, right? 40 RB and 8 RB on third order symbol. The 40 plus 8, 48 RB will allocate for the PBCH only. So total number of कितना हो गया? 48 कितना हो गया? 48 into 12 subcarrier हो गया, and 25% will use for the DMRS, right? So 25% will use for the DMRS, then 75% use for the payload. So 48 into 12 into 0.75, that means 432 resource element एलिमेंट ये PBCH पेलोड के लिए यूज होगा, राइट. सो PBCH यूज QPS के मॉड्यूलस, राइट. तो QPS के मॉड्यूलस हाउ मेनी बिट्स विल एलोकेट 2 bit, right. 432 into 2, that will be 868 bit will be utilized for the PBCH. Resource element occupied by the PBCH DMRS are dependent upon the physical layer cell identity. या PCI पर डिपेंड करता है. अगर PCI चेंज होगा DMRS का लोकेशन भी चेंज हो जाएगा. वो कैसे देखते हैं. DMRS occupy one in the 4 resource element, right. So already I have told DMRs take 25% space, or so 25 means out of the 4 RE, 1 RE will allocate for a DMRS. So the PCI mode 4, that is the formula to calculate or find the DMRS location. PCI mode 4 rule has been specified to determine its location, right. So UE is able to deduce the PCI from the primary and secondary synchronization. अब PCI कहाँ से मिलेगा. प्राइमरी या सेकेंडरी सिंक्रोनाइजेशन को डिकोड करेगा, PSS SSS को डिकोड करेगा, तो PCI मिलेगा. अब PCI मोड 4 रूल फार्मूला लगाएगा, then it will get the DMRS location, right. So then UE know where to expect the DMRS when decoding the PBCH payload. So अगर PBCH DMRS को डिफाइन करे तो बोल सकते हैं PBCH DMRS is a special type of physical layer signal which function as a reference signal for decoding PBCH. तो हम बोल सकते हैं PBCH DMRS is a special type of physical layer signal. एक सिग्नल है जो कि PBCH को डिकोड करने के लिए यूज किया जाता है. In LT we don't have the special type of signal because LT we use CRS, cell a specific reference signal for PBCH decoding. CRS यूज किया जाता है इन LT में, बट इन 5G में we don't use the CRS, we use the PBCH DMRS to decode the PBCH, right. So PBCH पे क्या मिलेगा, MIB इंफॉर्मेशन मिलेगा, सिस्टम इंफॉर्मेशन, सिम मैसेज मिलेगा. वो सारे को डिकोड करने के लिए एक स्पेसिफिक टाइप ऑफ सिग्नल चाहिए, राइट. सो LT में सेल स्पेसिफिक रेटेड सिग्नल था, सेल स्पेसिफिक सेल रेफरेंस सिग्नल. नाउ हियर इज द PBCH DMRS. यूज द PBCH DMRS सिग्नल एंड विल डिकोड द PBCH रिलेटेड इंफॉर्मेशन. तो ओवरऑल देखें तो आउट ऑफ द 20 RB means 240 sub carrier, 20 RB means 20 to 12. Out of the 240 sub carrier, 56 to 182 sub carrier used for the PSS on first wavelength ensemble. Remaining sub carrier 0 to 55 and 183 to 239 sub carrier used for set to 0 means no use of that sub carrier. And SSS, secondary synchronization signal, is used between 56 to 182 sub carrier, but it's for a third wavelength ensemble. And for the third wavelength ensemble, set to 0 is allocated for 48 to 55 and 183 to 191 sub carrier. So other sub carrier for third wavelength ensemble from 0 to 47 used for PBCH, and 192 to 239 sub carrier is used for the PBCH. So DMRS की अगर बात करें तो DMRS location, already I've told DMRS location is changed as per physical cell ID location. DMRS signal is required to decode PBCH because it is a special type of physical layer signal which function as a reference signal. एक स्पेशल टाइप का सिग्नल है जिसका यूज क्या है, इट इज स्पेशल टाइप ऑफ रेफरेंस सिग्नल टू डिकोड द PBCH को डिकोड करने के लिए इस DMRS सिग्नल को यूज किया जाता है जिसका लोकेशन फिजिकल सेल आईडी के अनुसार से चेंज होता है. इफ LT वी यूज द सेल स्पेसिफिक रेफरेंस सिग्नल, वी डोंट यूज PBCH DMRS टाइप स्पेशल सिग्नल. अगर फॉर्मूला की बात कर रहे हैं जो मैंने बोला PCI मोड 4 NID सेल मोड 4 NID सेल इज फिजिकल सेल आईडी V equal to. So the PBCH DMRS location move along with a physical cell ID change. यहाँ आप देख सकते हैं every 4 resource element में 1 resource element is allocated for the PBCH DMRS. We'll see the 5G NR physical cell ID. To find the physical cell ID, we use synchronization signal, right, to perform beta cell. So synchronization signal is primary and secondary synchronization. If we'll decode the PSS and SSS, then we'll get the physical cell ID. So PSS provide the radio frame boundary पोजीशन ऑफ फर्स्ट सिंबल इन रेडियो फ्रेम, जो उस रेडियो फ्रेम में जो फर्स्ट सिंबल है उसका रेडियो उसका बाउंड्री क्या है, देन विल गेट इट फ्रॉम द पीएसएस. एसएस जो है सेकेंडरी सिंक्रोनाइज सिग्नल जो है इज प्रोवाइड द सब फ्रेम बाउंड्री. द पोजीशन ऑफ द फर्स्ट सिंबल इन सब फ्रेम, सब फ्रेम जो पहला सिंबल है उसका पोजीशन क्या है ये हमको एसएसएस से पता चलता है, सेकेंडरी सिंक्रोनाइजेशन से. सो द फिजिकल लेयर पीसीआई जो है in using both PSS and SSS, that is the one formula is there in LT also have the same formula to calculate the physical SID, that is 3NID1 plus 3NID2. ID1 that is the secondary synchronization signal, NID1 get it from the SSS, secondary synchronization signal, right? So it is a range that is a range of 0 to 335, and NID2 that is give this information for primary synchronization signals. So and its range is 0, 1, 2. So here you will see 0 to 335, 0, 1 to 335. So this is the information, this is the location of the secondary synchronization signal. So this information 0 to 330 we will get it from the SSS, and PSS we will get the 0, 1, 2. So total number of physical cell ID is possible is 1008. So if we are calculating, suppose that in 5G and our SSS value is 303, secondary synchronization value is 303, and PSS value is 1. So the as per formula 3 into 303 plus 1, that is 9. PCI value is 910, right? So once you got the PCI, then you will get the PBCS DMRS signal, because DMRS location change as per with the PCI information, right? So now here in DMRS can be placed at a 4 different position in Ssb block, which is given by V. V is what the V is formula in ID cell mode 4. So in ID cell is physical cell ID. What physical cell ID we get it? 910 now, right? So 910 mode 4 equal to 2, then V equal to 2. So in this pattern of DMRS signal location is changed as per PCI. So V0, V1, V2, V3. So that now V is equal to 2, right? So the location of DMRS signal will be this. For the V is equal to 2. So this will be this is the DMRS location. The DMRS signal will allocate for this physical cell ID. So now UE PBCS DMRS signals. So UE measure the signal strength of demodulation of reference signal PBCS DMRS of each SSB, and it detected for a certain period from the measurement result. So UE can identify the best SSB index with a strongest signal. On the basis of the measurement, UE decided which one is the best beam, right? So that it decode the PBCS MIB content information such as SFN, SSB index, raster offset, DL numerology, RIMC configuration, DMRS location, and cell bearing related information. So all the things is decoded after reading the DMRS signals and PCI informations. So that after decoding, after reading, by using the DMRS reference signal, you decode the PBCH information where MIB and SIB is located. Now MIB and these are the configuration, these are the parameter related to the cells. Now MIB is decoded. So remain part I will discuss in next video. So thanks for watching this. Intention of this video is that how you know that where actually Ssb is located on carrier bandwidth 51 RV and what is the position from absolute frequency point A. मतलब ये है कि कैसे UE को पता चलेगा आखिर Ssb कैरियर बैंडविथ 51 RV जो है इस 51 RV के किस पोजीशन पर लोकेटेड है और एब्सोल्यूट फ्रीक्वेंसी पॉइंट ए है, इस पॉइंट ए से SSB का लोकेशन यह UE को कैसे पता करता है. So today in this video I'll explain about SSB in non-standalone mode and we try to decode SSB. So let's start. Hello friends, I am Anand from Anand Techno Solution. Today I am going to discuss about the Ssb in 5G NR standalone mode. In 5G NR, Synchronization Signal Block, that is Ssb, include PSS, SSS and PBCH, and its location compared to LT is completely different. In LT, synchronization signal position is straightforward and it is located around DC subcarrier. Where is the DC subcarrier? It is a center, a 6 PRB, that is 72 subcarriers allocated for a synchronization signal in LT. But in 5G NR, synchronization signals are positioned on bandwidth part and it is not fixed and can locate anywhere across the carrier bandwidth. LT में सिंक्रोनाइजेशन सिग्नल का लोकेशन फिक्स है. इट इज़ अराउंड द सेंट्रल फ्रीक्वेंसी 72 सब कैरियर is located, that is 6 PRB. But in 5G location is not fixed, anywhere can be in the bandwidth. Here we can take an example of 5G NR band N78 with FR1 and try to put together how the time domain and frequency domain resources are allocated for Ssb and how positioning of Ssb on carrier bandwidth is determined. Ssb time domain resources, Ssb block consists of 4 conjugative overhead symbol, right? So first symbol position is determined by combination of carrier bandwidth plus sub carrier spacing. So as per 3GPP table, from this table we can calculating the starting OFDM symbol of Ssb for subcarrier 15 kHz, 30 kHz, 120 kHz and 240 kHz. So in case a scenario, you can see that it is for a subcarrier spacing is 15 kHz and formula is to calculate the starting OFDM symbol of Ssb is 28 plus 14N, right? So that if a frequency is less than equal to 3 GHz, then N value is 0 and 1 and Ssb. So what will be the Ssb starting position? Ssb starting position will be, you can just put 0 and 1, then 2, 8, 16 and 22. So total number of beam will create for this frequency is 4 Ssb beam will form, right, for the if frequency is less than equal to 3 GHz, right? Next is if frequency is greater than 3 GHz and less than 6 GHz for sub carrier spacing 15 kHz, then what value will be? Then N value is 0, 1, 2, 3. Here you can see that 0, 1, 2, 3. Ssb starting position will be here. You just put in the formula 0, 1, 2, 3 and you can see here 2, 8, 16, 22, 30, 36, 44, 50. That means total 8 Ssb beam form for this frequency if greater than 3 and less than 6 GHz and sub carrier spacing is 15 kHz. Total number of Ssb form is 8. So what I am telling that a starting position is 2, 8, 16, 22, 30, 36, 44, 50. That is for the 15 kHz and frequency is greater than 3 and less than 6 GHz, right? So 2 means at starting position of OFDM symbol. That means 4 conjugative OFDM symbol. Every Ssb will take conjugative 4 OFDM symbol, right? So 2, 3, 4, 5, 2, 3, 4, 5. So 4 OFDM symbol, 5. After that again it will start from Ssb will start from 8, right? So 8, 9, 10, 11, 8, 9, 10, 11, continuous 4 OFDM symbol, right? So this is second Ssb. Third Ssb, where it will start? It will start from 16, 17, 18, 19, 16, 17, 18, 19. This is third Ssb. Fourth Ssb, where will start? It will start from 22, right? 22, 23, 24, 25. Okay. So next Ssb again, where from start? It will start from 30, 30, 31, 32, 33. Next will start again from 36, 36, 37, 38, 39. Like that Ssb form. So total how many Ssb will create for this frequency greater than 3 less than 6. Total 8 SSB will form, right? Next is SSB frequency domain resources. SSB in frequency domain consists of 240 conjugative subcarrier number in increasing order from 0 to 239. It's equal to 20 PRV, right? 20 PRV means 20 into 12, 240 subcarrier. That means it will start from 0 to 239. So if SSB subcarrier offset is not provided, so SSB is divided from the frequency difference between the Ssb block and point A. Ssb block and point A. SSB subcarrier offset is not provided. So SSB is derived from the frequency difference between the SSB block and point A. Now we'll understand where is the point A, where is the SSB block in the frequency and time domain and domain location. So in NSA mode, that means non-standalone mode operation, the location of the SSB is determined by the information provided by the higher layer in RRC configuration message. What are the suppose that in these logs you can see that here you can see that absolute frequency SSB, absolute frequency SSB is 634008, right? And frequency band list is 78 N78, and absolute frequency point A is 642722. This is absolute frequency point A. Offset to trigger equal to 0. Subcarrier spacing is 30 kHz and carrier bandwidth is 51 RB is located, right? So in initial downlink BWP, so location and bandwidth is 3750 and subcarrier spacing is 30 kHz. So this following information can be extracted from the above RRC message, RRC reconfiguration message. So band N70 is a TDD band, right? So known as a TDD 3500. If frequency range is 3300 to 3800 megahertz, right? For N78, 3300 to 3800, and it's belong to FR1. So and subcarrier spacing 30 kHz with carrier bandwidth 51 RB, which is 20 megahertz with reference to the here in this table you can see that subcarrier spacing 30 for the 20 megahertz bandwidth number of RB is 51 RB, right? 51 RB. And for 40 megahertz it is 106, and for 100 megahertz bandwidth total number of PRB is 273. So total PRB is allocated for subcarrier spacing 30 is total is 273 PRB will allocate if we use the higher bandwidth 100 megahertz, right? And here you can see the frequency range 0 to 3000, 3000 to 24250, and 24250 to 1 gigahertz. So and del F is the frequency raster, right? For 0 to 3000 raster is 5 kilohertz, and for second 3000 to 24250 15 kilohertz, and below 1 is the 16 kilohertz. So this is the frequency raster. Other is reference frequency is for the 0 to 3000 frequency if REF is 0, for 3000 to 24250 3000 is reference points FREF, like that. In REF offset value is 6 5.0 to 20160066. So this is the range of NREF. Now we will calculate absolute frequency point A, because absolute frequency point A which I have the AFCN, right? So we need to convert in megahertz. So absolute frequency A, what is the means of absolute frequency point A? So it represents the common reference point A, right? It represents the common reference point A. The reference point is the 0th RB, 0 RB of 273 RB. 273 in this table I have shown for 30 megahertz maximum total number RB is 273 RB. and 0 RB of 273. So 0 RB of 273 RB. So 0 RB, that means first RB, it is just below point, right? So that represent the point of the 0th RB of 273 RB. 273 RB जो है उसका जो जहाँ से 0 से स्टार्ट हो रहा है, तो 0 जो है एक रेफरेंस पॉइंट है, राइट? सो विच इज़ द सेंटर पॉइंट ऑफ RB 0, right? So absolute frequency point A, that is 642722, that is ARFCN. Now we'll convert in megahertz. So in megahertz, this is the formula: f ref offset plus del f global, right? This is frequency raster. Del f global into nref minus nref offset. What is nref value? Is 642722 minus nref offset, that is a reference point. So what is the reference point for the this table, this spacing? That is this value 600000. So while you will put this value and you will try to find out that this is the megahertz, 3640.83 megahertz bandwidth, that is the absolute frequency point A. Now absolute frequency point Ssb, right? Absolute frequency Ssb, it represent the center frequency of Ssb block. Ssb block का जो center frequency है, that is the absolute frequency Ssb. So Ssb block is 20 RB as a result, right? 20 RB is allocated Ssb. So 20 into 12, that means 40 to 47 carrier will utilize. So from the log, absolute frequency Ssb ARFCN is 643008, right? NRF. So we will convert in megahertz. So here you can see that absolute frequency Ssb 3000 plus 50 into 643008 minus 600000. So when you will calculate it, it will come 3645.12 megahertz, right? So carrier center frequency equal to total number of RBs. What is the total number of RBs? 51, right? From the RSRE configuration message. So resource block respond to center frequency 51 by what will the center point of 51 RB? So 51 by 2, that means 26. It is not exact exact center point, but it will be around 51 by 2, that means it will we will see in integer format. So 26. So center frequency equal to absolute frequency point A, absolute frequency point A plus 26 RB into 12 subcarrier, right? Absolute frequency point A is 0th RB of 273, right? 273 RB. So absolute frequency point A plus 26 RB into 12 subcarrier. So center frequency equal to 3640.83, right? Plus 26 into 12 into 30 kilohertz, right? So when you will calculate it, it will come around 3650.19 megahertz. This is the center frequency. Now position of Ssb from point A. Position of Ssb from point A. So offset to point is come. It will come in the sieve message. So if what how we can define the offset to point A? It defines the frequency offset between point A and lowest subcarrier of RB overlapping with Ssb. It defines the frequency offset between the point A and the lowest subcarrier of the RB overlapping with Ssb. So unit of RB is expressed as a 15 kHz for FR1 and 16 kHz for FR2. So next one is Kssb. It defines the frequency of RB0 of Ssb, and the unit of RB is expressed as the 15 kHz for the FR1 and 60 kHz for FR2. So frequency offset to Ssb from point A equal to offset to point A plus Kssb. So now we will try to calculate the Kssb. So difference between the Ssb center frequency, that is absolute frequency Ssb, and point A. So point A, what is absolute frequency point A? So here we will calculate between difference between Ssb center frequency and point A, that is 36415.19 0.12 minus 3640.83, that means 4290 kilohertz, right? So difference between the point A and 0 subcarrier RV0 of Ssb, right? Point A is the starting point right here. So a difference between point A and 0 subcarrier RV0 of Ssb, right? So 4290 minus 10 10 RB, that is the bottom of 10 RB of Ssb is 20 RB, right? So minus 10 RB into 10 into 12 into 30 kilohertz. So when we will calculate, it will come around 690. So we are calculating number of RB, we will convert in RB, 690 by 180 kilohertz. That means it will come around 3.8. Offset to point A value is 3, right? From the same message. So Kssb equal to 690 minus 3. Offset to point A is 3. 3 into 12 into 50 by 15 kilohertz, right? So it will come around, how much it will come? It will come around 10 subcarrier, right? It will come around 10 subcarrier. So offset to Ssb from point A, what will value? Offset to Ssb from point A से Ssb जहाँ पर start हो रहा है, what are the values? Offset to point A plus Kssb, so 3 RB plus 10 subcarrier. So this is the where Ssb will start. Ssb 0 subcarrier will be start from the absolute to frequency point A, from point A से 0 subcarrier. So this is the high. Okay, so thank you for watching this video. Bye, take care.